Welcome everyone to the online training, module number 4. I am Charles Yovu. Module number 4 will focus on quantitative data analysis for impact evaluation. And this module will begin with an introduction, and then we'll move on to look at the lessons that are covered in this module. Thereafter, we will look at lesson 1 of this module. As a matter of introduction, the purpose of this module is to help all the participants gain some basic knowledge of the various quantitative data analysis techniques used in impact evaluation. So just to look at the basic concepts of various data analysis techniques. Then we'll also specifically look at econometric techniques that are used in the analysis of evaluation data in more detail. It is expected that by the end of this module, participants have an understanding of the basic econometric techniques. For example, simple and multiple regression. Participants must also appreciate the basic concepts of quasi-experimental these techniques. You may recall that some aspects of this were covered in module 3. Further, participants are expected to demonstrate their ability to apply simple and multiple regression techniques to a real data set, then which can also be used in real impact evaluation data. Participants, finally, are also expected to demonstrate their ability to use quasi-experimental techniques to analyze impact evaluation data. So there will be some practical sessions where participants will be taken through the process of how to use some of these techniques using real data in Stata software. There are a number of lessons, specifically 7 lessons to be covered in module 4. And lesson 1 is simple regression analysis, which will form the foundation or will just be extended to the multiple regression analysis. Then we'll have to quickly look at introduction to experimental and quasi-experimental designs, which, as I said earlier, some elements of these were covered in module 3, and this will be more or less like a refresher, but now specifically looking at how we can apply such techniques in impact evaluation data analysis. Then we'll move on to propensity score matching technique, followed by difference in difference method. And then we'll look at instrumental variable regression. And we'll complete module 4 by looking at regression discontinuity design. Lesson 1, which focuses on simple regression analysis, will cover several subtopics. First, we'll look at the nature of regression analysis, then move on to simple linear regression, particularly a 2-variable model. Then we'll move on to the method of ordinary least squares, and then we'll complete the lesson with assumptions underlying the method of least squares but also we'll also focus on the concept of precision in regression analysis. Let's start looking at the nature of regression analysis. How did it start? When we trace the genesis of regression analysis, it is connected to Francis Galton, who conducted some experiments in 1885, particularly where he was looking at the heights of children from tall or from short parents, trying to measure the average of the heights of these children. And he observed that the average heights tended to regress towards population mean. In other words, the average heights, either from children from tall parents or of children from short parents, they tended to move towards the population average. And over the years, regression has taken over different meanings and application, but generally, regression analysis is understood as a technique that helps to establish the dependence of one variable, the dependent variable, on one or more other variables. These are independent variables. For example, we can look at the dependence of personal consumption expenditure on disposable real personal income. This is a common econometric or economic area of interest. I want to see how a household's consumption expenditure changes in relation to the changes in disposable income of the household. Another example could be the response of the demand for a product to changes in price. So this could be a marketing manager saying, how does the demand of our products change when we change the price of the products? Another example could be the dependence of crop yield. This could be rice or wheat or maize on factors such as temperature, rainfall, amount of sunshine, and fertilizer, just as an example, because there could be more other factors. So all these examples are examples where regression analysis can be applied to determine the relationships between these variables, dependent variable and the independent variables. Before we proceed, let's look at some key elements that we'll encounter again and again when we're working with regression analysis. So there may be statistics, relationships, and deterministic relationships. But we want to see the difference. Regression analysis focuses on the statistical and not functional or deterministic dependence among variables. What does that mean? Statistical relationships deal with random or stochastic variables. Variables that cannot be measured exactly because of some measurement errors, as we'll see later. So regression analysis applies to relationships that are not deterministic, but those that are statistical or stochastic or in other words, random in nature. Example, just similar to the examples we looked at earlier, the dependence of crop yield on temperature, rainfall, sunshine, and fertilizer. This is one of the examples of a statistical or stochastic relationship, in the sense that the explanatory variables, these are the independent variables such as temperature, rainfall, etc., will not enable the agronomist to predict crop yield exactly because of measurement errors and other factors that could be at play or affecting crop yield, but not taken into account in the analysis. In functional or deterministic dependency, we deal with variables, but these variables are not random or stochastic. They are deterministic. Another relationship that we must be focusing on is the regression versus causation. Do they mean the same thing? Regression analysis does not necessarily imply or help the evaluator to establish causation or cause-effect relationship between dependent and independent variables. It does not. In order to determine or ascribe causality between dependent and independent variables, an evaluator must appeal to the theoretical considerations. What are the theoretical understandings, considerations behind the relationship between the dependent variable and the independent variables? That's in the consumption expenditure example. One can invoke economic theory, which says that consumption expenditure depends on a real income. So with this theoretical understanding, then it may be possible to ascribe, to conclude cause-effect relationship between expenditure, consumption expenditure, and real income. Then let's also look at regression and correlation. Correlation analysis measures the strength or degree of linear association between two variables. And the correlation coefficient that is obtained is very important. For example, between smoking and lung cancer, we can establish the correlation, the association. Is smoking associated with lung cancer? So correlation can show us that there is association or no association. But correlation does not mean causation or cause-effect relationship. So we'll get a correlation coefficient which measures the strength of linear association between the dependent variable and the other variable, or between two variables rather. On the other hand, regression analysis estimates or predicts the average value of one variable on the basis of the fixed values of other variables. So regression analysis helps us to make predictions, to estimate average value of the dependent variable based on the given values of the independent or explanatory variables. While correlation will just show that these two variables are associated, they are moving together, either in the positive direction or in the negative direction. But do they cause each other, affect each other? Correlation analysis cannot do that. Further, in regression analysis, there is asymmetry in the way the dependent and explanatory variables are treated. The dependent variable is assumed to be stochastic or random. What does that mean? It means the dependent variable is assumed that it can take several values or can have a probability distribution depending on the values of the independent variables. On the other hand, explanatory variables are assumed to have fixed values at that particular time of the analysis. On the other hand, in correlation analysis, both variables are treated symmetrically. There is no distinction between the dependent and explanatory variable, or between the two variables where correlation analysis is being conducted. Let's also look at measurement scales of variables. There are different scales of measurement. This topic is particularly important to help participants understand the various nature of data that can be encountered during impact evaluation. So understanding the nature or characteristics or properties of the data that we encounter can also help during the analysis. So the first scale is the ratio scale. What does it mean? For a variable x, taking two values, x1 and x2, such that we can have a ratio of x1 to x2, or the distance, that is x2 minus x1, are meaningful quantities. There is also natural ordering, that is ascending or descending of the values along the scale. So ratio scale or data following under ratio scale will have these three properties. Property number one is that that data can be presented in form of a ratio. Two, that data can also help us determine the distance between the two data sets, and they make sense. But also, the same data sets will also have natural ordering. We can arrange them in ascending or descending order along the scale. So these three properties are very key and unique to the ratio scale. The second scale is interval scale. So data under interval scales will satisfy the last two properties of the ratio scale variables, but not the first. So the first was to look at determination of ratio. That is not possible under interval scale, but we can determine the distance between the two data sets, but also there's natural ordering. That's the distance between two periods. For example, the year 2000 and the year 1995 is meaningful. But we cannot take the ratio of the two time periods, like 2000 to 1999. That doesn't make sense. It's not meaningful. So the distance makes sense. The ratio does not make sense. But we can also see natural ordering. 1995, which is lower or area than 2000. Another example is temperature. So if one area, one district has recorded a temperature of 20 degrees, or another district has recorded a temperature of 40 degrees Celsius, we cannot say that district 2 with 40 degrees Celsius is twice as warmer as the first district with 20 degrees Fahrenheit Celsius. But we see that we cannot have a ratio of the two, but we have the distance in terms of one place being warmer and the other less warmer, but also natural ordering. But we cannot take the ratio of the two. And there are many other examples that fall under interval scale. Another scale is the ordinal scale. Here, the variable satisfies the third property of the ratio scale, that is natural ordering. But the distances between the categories cannot be quantified. And the ratios can also not be computed. Examples are the grading system. So if you have a grades for say maize or for wheat, so you have grade A, grade B, grade C, etc. These grades show natural ordering, but we cannot show, say, the distance between them or compute the ratios of the grades. Another example could be income class, upper, middle, or lower income, and many other similar examples that will demonstrate or show the natural ordering. But beyond that, there's not much that we can compute in terms of ratios or the distances between them. The last scale is nominal scale. Here, variables have none of the features of the ratio scale variables. So all the three properties that we talked about under a ratio scale, that's the ratio, the distances, but also the natural ordering, all those three properties do not apply under nominal scale. And examples here can be gender, okay, male or female, or marital status, we have married. Okay, so sometimes we assign numbers for gender, 1 representing female, 0 representing male. So those are just numbers for identification. Beyond that, they have no other meaning. Marital status, 1 can be single, 2 married, 3 divorced, 4 widowed, etc. So those numbers are attached just to identify one's marital status. Beyond that, they don't mean anything. Or if we go to sporting activities, football, okay, players put on jerseys with numbers, 23, 15, 8, 1. They are just there to identify the players. Beyond that, the numbers have no other meaning. So all those types of data fall under the nominal scale. Now, having looked at that data, as I said earlier, that understanding the nature of a particular data will help us to say what kind of analysis can we do, okay, in regression analysis, for example, and any other analysis. So looking at simple linear regression is also referred to as bivariate regression. Is regression in which the dependent variable, also known as the regressant, is related to a single or one explanatory variable, also known as the regressor. So we have two variables, one dependent and one independent. Whereas in multiple regression analysis, the regressant or the dependent variable is related to more than one regressors. Now, since our interest is to find the value of y, and y here represents the dependent variable, given the value of x, where x here is the independent or explanatory variable, as conditional expected values, which is symbolically denoted as expected values of y given the values of x. It is clear that each conditional mean expected mean value of y given the values of x is a function of x, where x is a given value, rather where xi is a given value of x. And symbolically, this is written or can be denoted as expected value of y given the values of x is equal to a function of values of x, which is dependent variable, where a function of xi denotes some function of the explanatory variables x. Now, this equation 4.1.1 is generally known as the population regression function, and sometimes is also referred to as the linear population regression function, or the model of the type expected mean value of y given x values is equal to beta 1 plus beta 2 xi. Now, in regression analysis, our interest is to estimate the parameters of a population, of the whole population, or to estimate the population regression function. That means estimating the values of unknown beta 1 and beta 2 on the basis of the observations on y and x. However, while trying to determine the value of the dependent variable y, it is not possible to consider all possible explanatory variables. As such, the estimated value of y cannot be exact. In other words, there will be some independent variables or some other factors that are affecting the dependent variable, but for some reasons, they will not be included in the model. As a result, there is deviation of the actual mean value, and the deviation is not denoted as ui. So symbolically, we can say y estimated value of I, rather yi is equal to expected value of y given the values of x plus the deviation mu I, where the deviation mu I is an unobservable random variable, also known as the error term or disturbance term, which can be either positive or negative value. So if expected value of y given the value of x is assumed to be linear in xi, then the equation 4.1.3 may be written as yi is equal to the expected value of y given the values of x plus the disturbance term or the error term, which is the same as equal to beta 1 plus beta 2 xi plus mu I. Assuming that yi is family consumption expenditure in our previous example as the dependent variable, then equation 4.1.4 shows that the consumption expenditure of a family yi is linearly related to its income, which is xi, plus the disturbance term mu I. The significance of the stochastic disturbance term or error term is that it represents the effect of all other variables that have not been included in the model. The sample regression function. In most situations or practical situations, it is not possible to observe population values or to estimate the population regression function. Because what we have is a sample of Y values corresponding to some fixed X's and not the population of Y values. Yet we need to estimate the population regression function, but this can be done on the basis of the sample information that is available. So the sample counterpart of equation 4.1.2, which was the population regression function equation, may be rewritten as the estimated value of y, I, is equal to estimate beta 1 plus estimate beta 2xi. In other words, y hat I is equal to beta hat I plus beta hat 2xi, which is similar to the population regression function. But here we are adding the hats on top to represent this model as a sample regression function or sample regression model, where y hat is read as y hat or y cap, and y hat is the estimator of expected value of y given the values of xi. Beta hat 1 is the estimator of beta 1, which is a parameter of the population, but beta hat 1 is an estimate of the sample. Beta hat 2 is an estimator of beta 2, where beta 2 is a population parameter. The error terms mu hat I is the estimator of mu I, which is the error term in the population regression function, is also introduced in the sample regression function. Now, let us look at the two variable regression model, particularly look at the problem of estimation. Since the sample regression function is an approximation of the population regression function, how should the sample regression function be constructed so that beta hat 1 is as close as possible to the true beta I? In other words, the sample beta value of beta 1 should be as close as possible to the value of the population beta 1. Similarly, beta 2 hat should be as close as possible to the true beta 2, even though we will never know the true beta 1 and beta 2. How should this be done? There are generally two methods that are used for this estimation. First is the ordinary least squares method and the maximum likelihood estimation or method. However, between the two, it is the OLS, the ordinary least squares method, that is extensively used in practice or in regression analysis, basically because it is intuitively appealing and mathematically much simpler than the maximum likelihood. So in our discussion, we'll mainly focus on the ordinary least squares method or estimation. The method of the ordinary least squares, look at the population regression function, which is not directly observable. So we estimate it from the sample regression function. In other words, we cannot observe the values of the regression function parameters, but we can only estimate those values using the sample regression function. And this sample regression function is given as y hat I is equal to beta hat 1 plus beta hat 2 xi plus the hat error term hat I, which can be reduced to y hat I plus the error term mu hat I, where y hat I is the estimated value of the population yi. But how is the sample regression function itself determined? So first we have to express equation 4.1.7 as mu hat I is equal to yi minus y hat I. So that's the difference between the population value minus and the sample value. The difference between the two gives us the error term or the deviation, which is equal to y hat I minus, we substitute y hat I with rather yi with the estimated beta hat I plus beta 2xi plus mu hat I. In other words, simple substitution, which shows that the mu hat I, or the error term, the estimated error term, are simply the difference between the actual and the estimated values of y. In other words, the difference between the population actual value and the estimated, that is the sample value of y. Now, given n pairs of observations on y and x, we would like to determine the sample regression function in such a manner that is as close as possible to the actual y. In other words, sample estimates must be as close as possible to the values of the actual values of y, or population values. So this involves choosing the sample regression function in such a way that the sum of the residuals, sum of the estimated errors, is equal to sum of y minus y hat I is as small as possible. In other words, we want to reduce the errors or estimating the population values from the sample values. That is done using the least squares method, which states that sample regression function can be fixed in such a way that sum of mu hat squared I is equal to summation of yi minus y hat I squared. This will then give us summation of yi minus beta hat I minus beta hat 2xi squared is as small as possible, where mu hat I squared are squared residuals or error terms. So the method of the least square chooses beta hat I and beta hat 2, beta hat I and beta hat 2 in such a manner that is, rather, the method of the least square chooses beta hat 1 and beta hat 2 in such a manner that for a given sample or a set of data, the sum of mu hat I squared is as small as possible. So in other words, the method of the least squares helps us to estimate beta hat 1 and beta hat 2 in such a manner that the errors are as small as possible. Thus, beta hat I is estimated by this equation. Beta hat 1 is equal to summation of xi squared multiplied by summation of yi minus summation of xi multiplied by summation of xi multiplied by yi divided by n summation of xi xi squared minus bracket summation of xi squared. This will give us y bar minus beta hat squared times x bar. So in other ways, to estimate beta hat 1, we can simply just take the difference between y bar, which is average value of y, minus beta hat 2 x bar. On the other hand, we can estimate beta hat 2 using these notations, where beta hat 2 is equal to summation of small xi, small yi, divided by summation of small x2 squared I, which will give us summation of small xi, yi, divided by summation of xi squared minus nx bar squared, which will give summation of xi, yi, divided by summation of xi squared minus nx bar squared. So if we were to compute these manually, that's how beta 1 hat, beta 1 hat and beta 2 hat would be estimated. Now the estimators obtained are known as least squares estimators, because they are derived from the process of the least squares or the least squares principle. So the values of beta hat 1 and beta hat 2 obtained through these processes are known as least squares estimators. Now let's move on to the assumptions that underlie linear regression models, specifically the method of least squares. There are several assumptions underlying the method of least squares. Since the dependent variable yi depends on both the xi and the error terms I, ui, the assumptions made about the xi variables and the error terms are extremely important for the valid interpretation of the regression estimates. In other words, an interpretation of the estimates from these regression analysis depends on understanding of the assumptions underlying the method of the least squares. Assumption number 1, linear regression model. So the regression model is linear in parameters, though it may not or may be linear in variables. That is, the regression model is linear in parameters, though it may or may not be linear in variables. So what are these parameters? Beta 1 and beta 2, these are parameters. They have to be linear, though the variables, that is xi's, may not be linear. Assumption number 2 is fixed x values or x values independent of the error term. That means values taken by the regressor x may be considered fixed in repeated samples, as is the case of the fixed regressors, or they may be sampled along with the dependent variable y, in the case of stochastic regressor. In the latter case, it is assumed that x variables and the error term are independent. That is, the covariance between x variables and the error terms mu I is 0. There is no, the variables and the error terms are independent. In other words, they do not affect or influence each other. Assumption number 3, 0 mean value of disturbance, mu I. That means the mean value of mu, conditional upon the given x value is 0. Symbolically, we can say expected value of the error term given x values is equal to 0. Or if x is non-stochastic, the expected value of the error term mu I is equal to 0. So the implication is that there is not specification bias or specification error in the model used in empirical analysis. So here, it is assumed that the value of the error term is 0. In other words, the model is specified exactly without any errors or any bias, so that the error is 0. That's an assumption. Assumption 4, heteroscedasticity or constant variance of UI or of the error term UI. The variance of the error or the disturbance term is the same regardless of the value of x. In other words, it does not change, it remains constant. Symbolically, this can be given as the variance of UI is equal to expected value of UI minus expected UI given xi bracket squared, which is equal to expected UI squared given the value of xi because of assumption 3, and UI expected UI squared if xi are non-stochastic. This will give us the variance. So here, the key point is that the disturbance term remains the same. The variance of the disturbance term or the error term remains the same or is constant regardless of the values of x. Assumption number 5, no autocorrelation between the disturbances. So given any 2x values, xi and xj, where I is not equal to j, the correlation between any 2 error term, ui and uj, where I is not equal to j, is 0. In other words, there is no correlation. In short, the observations are sampled independently. So if there is no correlation between any 2 error terms, that means their value is 0 correlation. Symbolically, covariance of ui and uj given values of xi and xj is equal to 0. No covariance or no correlation between the error terms. Covariance ui, uj is equal to 0 if x is non-stochastic, where I and j are 2 different observations, and where the covariance means, where the cov means covariance. So the key point here is that there is no correlation okay, between the error terms to any two UI and UJ. Assumption number 6, the number of observations n must be greater than the number of parameters to be estimated. Put differently, the number of observations must be greater than the number of explanatory variables. Now, having looked at those 7 assumptions underlying the ordinary least squares method, which must be used while interpreting our estimates, let us now move on to precision or standard errors of least squares estimates. Since the sample data are likely to change from sample to sample, the estimates will also change ipso facto. That means from sample to sample as well. Therefore, what is needed is some measure of reliability or precision of the estimators beta hat 1 and beta hat 2. In statistics, the precision of an estimate is measured by its standard error given as SE. The standard errors of ordinary least squares estimates can be obtained using the following notations. Variance of beta hat 2 is equal to sigma squared, which is variance squared, divided by summation of x squared I, or xi squared. Now, if we take the square root of both sides, square root of variance is standard error of beta 2 hat, which is equal to sigma divided by square root of summation of xi squared. That will give us the standard error of beta hat 2. In order to obtain the standard error for beta hat 1, we use the following notation. Variance of beta hat 1 is equal to summation of xi squared divided by n summation of xi squared multiplied by sigma squared, or variance squared. If we take the square root of both sides, on both sides, we get standard error of beta hat 1, which is equal to square root of summation xi squared divided by n summation xi squared multiplied by sigma. So that means we have standard errors for both beta hat 2 and beta hat 1, where var is the variance and SE is standard error, and where sigma squared is the constant or homoscedastic variance of UI. This sigma squared itself is estimated by the following formula. So sigma hat squared is equal to summation of mu hat I squared divided by n minus 2, where n minus 2 is degrees of freedom. We'll look at it shortly, where sigma hat squared is the OLS, ordinary least squares estimator of the true but unknown variance, sigma squared, and n minus 2 is known as the number of degrees of freedom, df, and summation mu hat I squared is the residual sum of squares, RSS. Once the sum summation mu hat I squared, or the residual sum of squares, is known, then sigma hat squared can be computed. Summation mu hat I squared can be computed from the following. That is, summation mu hat I squared is equal to sum of yi squared minus beta hat 2 squared multiplied by summation xi squared s. Also note that the positive square root of sigma hat squared will give us sigma hat, which is equal to square root of summation of u hat I squared divided by n minus 2, which is the degrees of freedom. And this is known as the standard error of estimate, or the standard error of the regression, SE. Now, these are the processes when we are computing these estimates manually. But all these values, the error terms, the values of the estimated beta hat 1, beta hat 2, can be automatically generated using software such as the Stata. But this gives us a picture of how the different processes that are involved when we want to get the various estimates. Now let's quickly look at the properties of the ordinary least squares estimators. An estimator, or OLS, or ordinary least square estimator, B hat 2, is said to be best linear and biased estimator, commonly known as blue, of B2, if the following hold. So in other words, an OLS estimator is said to be blue, that is best linear and biased estimator of a population parameter, if the following hold. Number 1, it is linear, that is a linear function of a random variable, such as the dependent variable y in the regression model. Number 2, it is unbiased, that is its average or expected value of beta hat 2 is equal to the true value of beta hat 2. Number 3, it has minimum variance in the class of all linear unbiased estimators. That means an unbiased estimator with the least variance is known as efficient estimator, because it has least or smallest deviation. So an OL estimator that meets these conditions is said to be blue, best linear and biased estimator. Then lastly, let's look at the concept of the coefficient of determination, R squared, which is also known as a measure of goodness of fit. So the goodness of fit of the fitted regression line to a set of data is concerned with how well the sample regression line fits the data. If all the observations were to lie on the regression line, we would obtain a perfect fit, but this is rarely the case, at least in practice. So generally, there will be some positive error terms, estimated error values, and some negative estimated error values. So the coefficient of determination, R squared, that is small r squared, which is used in a simple regression analysis, in the case of 2-variable regression analysis, or the capital R squared, which is used to represent coefficient of determination in multiple regression case. This coefficient of determination measures how well the sample regression line fits the data. In other words, when we have fitted the sample regression line, we have applied the sample regression model to a set of data, the coefficient of determination helps us to determine how well that same sample regression line fits the data. To what extent do the variables included in the model explain the variation in the dependent variable? It measures the proportion or percentage of the total variation in Y explained by the regression model. So once we have run the linear regression model, the coefficient of determination helps us to make a judgment or decision. How well has this sample regression line fitted into the data? How much of the variations in Y have been explained by the regression model or by the variables collectively included in the model? So this coefficient as well is automatically generated in Stata, but that is how it is interpolated, which then can be used to judge whether our model fits the data well or not. And the coefficient of determination has two properties. Number one, it is a negative quantity. So coefficient of determination cannot be a negative value. Number two, its limits are that it ranges from 0, it must be equal or above 0, or must be equal to or less than 1. So it ranges from 0 to 1. If the coefficient of determination is close to 0, for example, 0.025, okay, it means our fitted sample regression model explains a very small percentage of the variations in Y or in the dependent variable. On the other hand, if the coefficient of determination is 0.9562, which is close to 1, it means our fitted sample regression line or model explains about 95% of the variations in Y or dependent variable. So comparing the two, the 0.02 explains a smaller percentage, while the other one explains a higher percentage, which means the sample regression line, which has a higher coefficient of determination, fits the data better than the one which has a lower or a small coefficient of determination. Thank you for your attention.